Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be talking about stack smashing. So this is going to be a little bit of an unusual lecture. I don't have any formal slides prepared for this one, and this is not something that's going to be covered in the final. Consider this as sort of a bonus lecture. We're going to be seeing how we can use the knowledge we've gained this second half of the semester about how compilers work to exploit how memory is laid out in a process to actually execute arbitrary code on a machine by hijacking the return address of functions. Now, before I begin, I want to show the course website, the specific page here, the stack smashing page of the course website. There are some nice links on here. So there's this old article, rather old article about stack smashing. I haven't read it, admittedly. I think I read it maybe a while ago. I can't remember. It looks like a good article. Typically articles like this, written by some old hackers, are pretty good. There's a link to this tutorial we're going to be following today. So we're going to be actually executing a stack smashing attack. And there's this 3-part tutorial we're going to follow. I have the notes written down, so we'll go through it step by step. And there's the GitHub repo right here. This is from Dr. Paul Gazzillo, the professor who originally created the course that I've been teaching this semester. And in this repo, you can see the instructions for executing the attack, links to the blog post, and some files for setting everything up. And we'll see more of that later. But if you want to actually follow along and execute these attacks yourself, this attack yourself later, I recommend doing it. Just clone this Git repo and you can actually try it out. And finally, there's this website, pwn.college. I'm going to go to this one here and actually show you what it is. This is basically like training for hacking. Like you can just practice your hacking skills. You start off with like simpler problems, move on to more and more complex ones eventually. So cool to try out if you're maybe interested in like cybersecurity. Okay, so with all that prelude information out of the way, let's focus on actually stack smashing. So I'll make that full screen. And I'm going to scroll down here. And first of all, let's take a look at what stack smashing actually is. So let's say we have some C program here on the left. So some C code here on the left is what we're looking at. And on the right here is some crude diagram roughly representing the stack layout of this C program. So, we learned about the stack this whole semester, how memory is laid out in the stack for each function. Each function gets its own stack frame, each function call. This diagram here sort of roughly represents what the stack frame for this C code would look like. So we have our return address, some parameters above it, assuming this function that we are in the middle of execution of had 8 parameters. We would have the 7th and 8th parameter on the stack. The first 6 are going to be stored in registers. We have the return address here, like I said. Old RBP, you'd probably have the RBX value pushed here too if you're following the x86-64 System 5 ABI. We'll leave it out for now. And what I want to do is step through this code. So you can see we declare some variables, y, x, and r, an array, so we have them laid out in their corresponding locations in memory. And the first thing we're going to do is read the value just read a value from user input into y. And we're going to assume that the user passes in the number 2 into y. So let's copy that and put it over here. So I'm going to copy this and paste it. And I'm using copy and paste manually and not using keyboard shortcuts because I'm actually using my left hand to hold my mic. So we're putting a value 2 into the variable y. Then for x, we're just storing the value 3 in there. So I'll put that in here, change that to a 3. And for this array variable, you'll notice that it starts here but grows upwards. Or rather, I guess, downwards in the stack, but upwards in memory. So remember, the stack grows down, and the high address is the base of the stack. So this is the high address, this is the low address, closer to 0. Stack grows downwards. But variables, like array variables, they actually start, the beginning of the array is going to be closer to the low address. And the reason for this is because it lets us as programmers access arrays using positive notations and have that match what actually goes on with the stack. So we use positive indices, right, to access values in these arrays. So if the stack grows closer to the low address, then a positive index will actually go closer to the high address. So that's why these positive offsets are going to get us going higher up here. And if you're kind of confused about what that looks like, let me draw out some pseudocode here. So if we want to access the value at index I for an array, this is sort of similar to saying we want to dereference the value at memory address R, ARR, plus 32 times I, assuming that integers are 32 bits on this machine. And you don't have to really do this in C. C will handle this arithmetic for you. But this is kind of like roughly what's going on. And so again, we're adding a positive offset here, plus 32 times I. And because that's positive, we're going to be going higher up on the stack. So that's why array 0 is here. The array and R sub 0 are equivalent essentially. So I could actually write, I could say asterisk R, and this is equal to R0. Because we're getting a 0 offset from the array variable. So without an offset, it's equivalent to just ARR. So that's why when we have these positive indices, we actually go apparently higher up in the stack. Okay, so let's actually use that here for these next instructions. So we're going to assign 1 to the value at index 2. So I'll copy this, paste it in right here, but that'll be a 1. And then index 0, we're placing the value 2. Oops, let me copy that, paste it in. Yeah, put the value 2 right there. And then we're going to print the value of the array. You can imagine this would probably print something like 2, whatever was in 1, and then 1. And then we're going to say R array sub y 0. So y is 2. We're going to go to index 2 of the array and set it to 0. So what could go wrong here? Well, there's two big issues with this code. One thing that's not really an issue necessarily is that we're accessing array with the index using y as an index for this array variable. That's not necessarily a problem. The problem is that we're reading y from user input and we're not actually checking it. We're not filtering it or sanitizing it. We're not making sure it's a valid index for this array's bounds. So what could happen here is that a user could actually pass in some malicious value, like we could say 6, and then we would be accessing the sixth index of array here. So let me actually put this back to where it was. So that R sub 2 should still be 1. This is now going to be 6, we'll say. And now if we go up the stack here, 0, 1, 2, 3, 4, 5, 6, what do you know? We've just written 0 to the return address. So I'll just put 0 here. So now when this function finishes executing, according to the ABI, if it's following the ABI correctly, by the time it goes to call the ret instruction, execution will jump to address 0. The instruction pointer will be set to address 0. And that's not right. You're going to get a seg fault that way. And that's kind of like the most harmless thing that could happen, is that your program gets a seg fault. And you might see this sometimes in your own C code if you accidentally overwrite some value that you shouldn't. This notion of reading a value from a user and having that affect parts of your program in a bad way, this is called like taint analysis, when you're trying to analyze parts of your program that could be tainted by user input. This is like a whole field of research into preventing these sorts of malicious inputs from having any sorts of like nefarious or disastrous effects. So that would be like taint analysis. Now, in this case, it's pretty harmless. Like the taint is not really a problem because we're just going to address 0 and getting a seg fault. That's annoying, but it's not the end of the world. But attackers a long time ago realized that if you knew this stuff about how memory is laid out, you could exploit it to actually set this return address to whatever you wanted. So let's actually look at an example of this. So again here, if we have some array, some char array, and we're reading into it, we could read more bytes than we have necessary and actually write garbage into this return address. So again, we get a seg fault here. But it's not always going to be garbage. So let me actually zoom in here a bit and try and explain this next example. All right, so that's nice and large. Cool. So what we could do instead is with this payload we're packing in. So let's say we have, I don't know, a read call that we're making. So remember from my shell how you use the read and write syscalls to read and write from standard in and to standard out. So likewise here, because remember, let me actually open the man pages here for a second. Remember that the read syscall accepts the buffer that it's reading into and a size as well. But if you specify a size larger than the size of the buffer, it's just going to be overridden. So in this example right here, you can imagine somebody made a call to read. They invoked the read syscall, and they read way past the size of this array and overrode the return address and beyond. And what we can actually do is, if we're trying to attack this program, we can fit not just code to overwrite the return address, but also the code that we actually want the return address to jump to. So we could actually fit like assembly code inside of our payload here. I'm calling it payload, this extra content that we're reading into this array. And we can overwrite parts of the stack, put it somewhere else in memory, and then alter the return address to jump to the beginning of the assembly code that we've packed into this overread. And this is kind of what we're going to be doing for this attack I'm going to demonstrate shortly. But not quite, so there's an extra wrinkle here that I want to convey, so hopefully it's clear by now. We're going to be fitting, normally what you would do is you'd fit a payload into this message you're sending and overflowing the buffer with, and then you alter the return address to jump to that malicious code. But what we're going to be doing is a little bit different. We are going to be modifying the return address, but we're not going to fit our payload in a content that we're reading in. Instead, we're going to be modifying the environment first. So you might have seen environment variables already. I think we've talked about them in class before. Like for instance, let me open up another terminal window here. So like a really commonly seen environment variable would be path. The path variable lets you run programs without specifying their full path. So for instance, because my let's see here, user bin directory is on my path, I can run programs in my user bin directory, like ls for instance, without needing to specify the whole path, user bin ls every single time. So there's all these different environment variables that a program has access to, and the way they get stored in memory is going to be on the stack as well when a program starts. They're actually going to be stored somewhere, I think above main. I'm not sure exactly where it is, but it's somewhere like either above or directly below the local variables of the main function. And if we know that, then we can actually store a malicious payload, some malicious assembly code, in our, or malicious object code, I should say, in our environment variable, overwrite the return address by overflowing some buffer, and then changing the return address to jump to the address of that environment variable which has our malicious code in it. And this is what we're going to be doing for this lecture. So I guess for the second half of this lecture, for this presentation, we're going to be overriding this array here, overflowing it, going to this return address, modifying it to jump to this environment variable that we're going to have that is going to contain some evil object code that we want to run. And some things I want to point out here is that we're going to make a few assumptions. We're going to have to remove some safeguards because these attacks have been known for decades, and there's like a rich history of people defending against them. For instance, let me actually show this here. So in the academic community for cybersecurity research, there's these papers published called Systemization of Knowledge, SOK papers, where researchers take a broad array of knowledge from the past like decades perhaps, and they try to synthesize it all into one succinct or concise paper that describes the state of some area of research. And this one has a really cool name, Eternal War in Memory, where they describe the history of attackers discovering ways to exploit memory and defenders finding ways to protect against those exploits. And they make a case that the memory of computers is just an eternal battleground. And it's a really cool paper to read, just for the title alone, I think. And what that has implications for us here is that we have to disable some of these protections that these attackers have these defenders have accumulated over the years against attackers. So one of these things we have to defend against is canaries. or we have to disable for our attack to work here as canaries. So what is a canary? Well, you might have heard the expression a canary in a coal mine. So back in the day, when miners would go into a coal mine, it would be potentially low on oxygen or even poisonous, and they needed a way to detect when that was happening in the coal mine, if there were like fumes being released by the minerals they were mining, or if oxygen was running out. They needed a way to detect this before there was too little oxygen for the miners to even breathe, because it kind of would creep up on you and you could just suddenly die of asphyxiation. The way the miners solved this problem was by putting canaries in cages and bringing them down to the mines with them. And what would happen is the canaries, because they're so much smaller, have such smaller and more sensitive lungs than humans, they would die much sooner due to asphyxiation when there was low oxygen or there was poison in the air. And so the miners would use that canary as a warning that they needed to get out of that mine or else they would die too. So computer scientists, or researchers I should say, have sort of borrowed this terminology to paint a vivid picture here with this mechanism called a canary, a stack canary. And what a stack canary does, or what it is it's placed right next to the return address in a function. And the idea is that if a attacker tries to modify the return address by executing a buffer overread, reading too much data into a buffer so that it overwrites the return address, then the canary is going to be modified. And if the program detects that the canary is modified and there's a canary present, then it stops execution with a permission, a security violation. So for our attack to work, we have to disable canaries because we're doing a buffer overflow. So that's one thing we're going to have to remove for our attack to work. Another is that in GCC, the stack is by default now not executable. So GCC will often, or modern GCC versions of GCC, when they compile your code, they will disable the execution of anything present in the stack. So even though we could set the return address to this evil code here, stored in this environment variable, if we compile their code with just basic GCC, no extra flags, this environment variable would not be executable because it's in the stack. So we're going to have to pass a flag to GCC to disable the, to enable the execution of code in the stack, not disable it, which is the standard now for security reasons. The final thing we have to take care of is address space layout randomization, ASLR. This is where the addresses of functions are randomly placed throughout memory. This is to prevent attackers from finding a specific address and then being able to target that address for exploits like this, where you execute arbitrary code. So we're going to have to disable that so that all their function return addresses are at fixed locations so we can actually exploit them. Okay, and before we begin, so we're almost ready to start, I think, I want to just point out that all these ideas we're going to be covering, this attack we're going to be covering, and these ideas we're covered so far, they don't just apply to CLIs, command line interfaces, command line programs, like we've been writing so far in this course. Like you could think somebody being able to exploit your MyShell program by using some kind of buffer overread, but there are more ways in which a program can be exploited than just a CLI. So for instance, if you're accessing a web application, let's say you're on your machine and you make a HTTP GET request to the index.html file of some website, maybe the course homepage, for instance, then your request is going to go over the internet, go through some DNS stuff, and then it's going to reach a web server. In this case, I'm going to assume like an Apache web server. I think some of UCF's servers are Apache servers, I'm not sure. And this web server, in this case Apache, which is again a web server, is going to respond back to your machine. And even though this is different, this looks different than what's going on with MyShell, where this is all in the command line. What's going on with Apache here in this web server, this communication over the internet, is in principle the same. You're sending some information to some destination, and that's going back to you. Now, what could happen is that the web server is probably, it's written in C code. I think the Apache web server is written in C. It could accidentally overread too much data from some requests you send it, and then you can actually execute a buffer overflow attack on some remote machine this way, because they're making read requests as well. The only difference is they're not reading from files, they're reading from sockets, TCP I think ICP sockets, in this case, would probably be what they're reading from and writing to. So big idea is that these attacks, they are not restricted to just like command line tools. These same principles apply to web servers, other kinds of tools that make remote connections. Anything that has to read from some kind of data source and then has a risk of overwriting a buffer, this kind of attack could apply to. All right, so I think with all that out of the way, let's hop into some code. So I have a terminal window open here. Okay, cool, I am recording. Let's take a look at what's in this directory. So this is the directory I showed earlier, that GitHub repo with the attack stuff in it. We have this code directory for some code we're going to be using for this demonstration, a Docker file and Vagrant file for setting up virtual machines for actually executing this attack. So if you don't know what a virtual machine is, it's like a way to virtualize and simulate execution of another CPU, another operating system even, on your own machine in like a virtualized environment. And it's kind of like, maybe think of like an emulator for playing games if you ever used one of those, except a little less fun. That's basically what it is. We have a README file with instructions on how to do this, how to execute this attack. I'm going to be referring to this because there's a lot of steps and I don't have them all memorized. And then the setuid.c file. This actually I want to show now. This is a bit more background that I think is relevant for this attack. In order for this attack to work, we need to exploit the fact that some programs which do not run with root privileges can be elevated to root privileges depending on who they're owned by. So let me give you a demonstration. Let's look at this file here, setuid.c. So in this file, setuid.c, we're making a call to this syscall here, getuid. So I know, you probably thought we were done going over syscalls. Like, I thought we were finally over with syscalls. No, we got a few more here just in this lecture. So we're calling getuid here. What this syscall does is it gets the real ID of the user who I believe started this process, is what UID is. So let me run this here. Yeah, get real user ID of the calling process. And then we have another call here, get EUID, which gets the effective user ID of the calling process. So UID is the one who created it. EUID is the one whose permission bits are set for this process when it runs. And we'll see that shortly, what that looks like. What we're going to do here is set the UID to the real user's ID. So whoever created this process, we're going to set these processes' effective user ID to the one who created it. And here we'll get the same values again and then print them out after doing the set EUID call. Now let's see what this would actually look like in practice, what the application here is. I'm going to compile this code with just gcc-o setuid setuid.c, and now if I do ls, you can see that setuid binary is there, and if I run it, it says that my real user ID of this, the real user ID of this process was 1000, the effective user ID is 1000, real user ID is 1000, and effective user ID is 1000. So nothing changed. My user ID is 1000 on this machine, in this machine here, and nothing changed because the owner of this file, or the effective user ID of this file, is the same as the real user ID. But we can change the file's effective user ID by using the shell commands change owner and change mode. So let's do that here. So I'm going to change the owner of this file to root. And now what I'm going to do is use change mode to specify the set UID bit for this file so that the file's effective user ID becomes that of the owner of the file when it runs, of this process when it runs, when this file runs as a process. The way we do this, set this user ID bit, is to just say u plus s. This is the shorthand for set the user ID bit for our user for this file. And now if I run stat on this file, you can see the permission bits are set to RWS. So normally we see like either nothing here, a hyphen, or an X for execute, but we see an S here. And the S means that we have the set UID bit set and the process is executable. So the program is executable, the file. And if I do ls, you can actually see it's in red. I don't know why my file explorer displays files with the set UID bit set as red, but it does. Maybe because it's a bad idea. I don't know. So let's see what happens now if we try to run this file, this program. You can see that the real user ID, the ID of the person who started the process, me, is 1,000, but the effective user ID of the process is 0. So that means that this process has like root privileges when it runs. But then after we call set UID here on the right, set effective user ID on the right here, we've actually changed the effective user ID back to that of the real user ID, which is 1,000, my user ID, so it goes back to 1,000. So what does this mean for us in our attack? Well, it means that typically attackers, they want to try and exploit a program which has this set UID bit set for it. And we can actually find which of these programs there are. So if I were to run ls-l, I can see like a summary of all the different bits of all these files in this directory. I'll zoom out just a little bit so it can be more clear what's going on here. You can see like all the files and their bits. So I can actually grep in my user bin directory for any files that have RWS set as their permission bits. And we can see that on a normal Linux machine, Linux installation, or at least Ubuntu, my distro, there are several files in our bin directory which have this user ID bit set. So like su does, sudo does, umount, password. They need to run as root in order to execute for some reason. They need to run as root. So they have this S bit set so that they're able to, while they execute, run as root with root privileges. And it kind of makes sense for sudo, right? Because the whole point of sudo is to super user to do things as a super user, as the root user. So of course you'd expect them to have the bit here set, the set user ID bit set. The downside is that these files all become like, targets for attack. Yeah, so anything that has a set UID bit set is going to be an attack target. And we're actually going to be using a program in this example now that has the set UID bit set as the one we're going to be exploiting. Okay, so now that we've reviewed set UID, I think all the pieces are in place. We can start to actually walk through this attack. So we're looking at the attack now, and this is the instructions on how to execute it. Because again, I can't memorize all these steps, so I'm going through the instructions one at a time here. Let's first, I've already built the Docker container, so we can skip this step. But let's actually run our container. So what this will do is actually hop inside our container. Oh, actually, before I do this, I'm going to turn off the address space layout randomization. So I mentioned that earlier. If I don't do this, then this example won't work. So I'm going to turn it off now for my machine just for this demonstration. I have to remember to turn this back on after I'm done with this lecture, or else my machine will be much more vulnerable. So it's off. And now what I'm going to do is, let's see, actually start the Docker container. So let's hop into that now. Okay, so now we're actually in our container. What's in here? Well, there's this PEDA directory. That's for a dependency for a tool we're going to be using for this example. And the stack smashing directory contains the code we're actually interested in here. So let's hop into this. There's some C files. There's some Python scripts. We'll go over these shortly and see what they all do. For now, let's run make to actually compile these C programs here. Okay, so you can see we got a few C programs compiled. Get env adder, classic.debug, and this classic binary, which, as you can imagine, since it has the red display that I mentioned earlier, has the set UID bit set. So this is going to be the binary that we're going to be targeting for our attack. But what does this actually contain? So let's see how this attack is going to work now. Let's jump into this classic.c code. So here's the source code for that file. You can see we had to compile it with the fno stack protector to enable or to disable canaries, and then the exec stack flag to enable stack execution. And here, disable ASLR, we already did this. What does this code actually do? Well, the first thing it does is print out some message, try to exec bin sh, like taunting us. And then we go to this function here, we call this function vuln. And in this function, we have a buffer of size 80, an integer variable r, and we store the result of read into r, and we read from standard in, 0 is standard in, into the buffer, and we read 400 bytes into our buffer. So this is pretty clearly a buffer override, right? Overread, I should say. We're reading 400 bytes into our buffer, whereas our buffer only has the space for 80 bytes. So this is a pretty blatant example, like not realistic at all, but you can imagine how in real applications when numbers and sizes get confusing, you can see like there are accidental buffer overrides occurring. But for our example here, we're just going to assume this really easy, obvious buffer overwrite of 400. So we're going to print the message, read a number of bytes, and then say no shell for you, and then return 0. Now the goal of what we're going to be doing here is, again, let me go back to the slides. We're going to try and change this return address to jump to the address of some environment variable that we're going to be storing before we execute our code. And we'll get to that shortly. So this function vuln is, as the name would suggest, vulnerable. So now let's start actually executing our code here. So we ran make. Now we're going to generate a sequence of 400 letter A's, so we can actually see how we're reading this data into memory and overwriting the stack with it. So this script here, normal.py, it just creates a buffer consisting of 400 letter A's, opens a file, normal.txt, and then writes to that file. And you can see it's actually just, consists of 400 letter A's. So that's exactly what we would imagine. Now what we're going to do is run GDB, the GNU debugger, with the PEDA Python Exploit Development Assistant extension to actually examine the contents of memory in our program. So let's do this now. I'm actually going to, before we start, I'm going to reopen the instructions here on the right on the bottom of the screen so that it's easier to read both sides of the screen. All right, I think that's much better. So GDB, and we're going to run the classic program here. Actually, classic.debug. We're going to run the debug version first with debugging symbols. Now we're inside GDB. We can set a breakpoint to stop execution of the program at a certain point. We're going to say break at line 13. So what this will do is stop execution at line 13 of this file classic.c. Line 13 contains the return instruction for that vuln function that we saw earlier. And now we're going to run this program with the R instruction in GDB, and we're going to read in the contents of normal.txt when we go to run it. When we do this, you can see the program reaches its breakpoint, and once the breakpoint is reached, we get a nice color-coded or colorized output describing the registers of the program, the code, and the stack. So if we look at the stack, we can see on the stack, there's the letter A repeated a whole bunch of times. And in the registers, we can see there's the value, where is it? Right in, let's see, RIP, no. Yeah, right here, RSP. The stack pointer actually has A repeated many times as well, and so does RBP. So if we're looking at like the stack layout here, you can imagine RBP was probably below the return address. We overwrote the return address and everything, their RSP as well, with everything in this with all these letter A's. So it seems like our stack smashing idea is sort of correct. We have managed to fill this stack with garbage. We're right here in the instructions, so we're at the move instruction. And let's see. Okay, if I press C to continue, we get a segfault because we've overridden the return address with some garbage data. Now I want to run this again, and we have our breakpoint. And before I resume now, I'm going to run this info frame command, so we can actually get a view of the stack frame, and we can see clearly that the saved instruction pointer is has been overridden to hexadecimal 414141. What is hexadecimal 41? Well, that's 64 plus 1, 65. The ASCII value of the capital letter A is 65. So this is actually A. So it seems like we have successfully overridden the instruction pointer and the return address and everything with all our A's. So now how can we actually take advantage of this ability to overwrite the buffer? So I'm going to quit GDB. And before I go back into it, I want to show this other file we're going to be looking at here. Actually, well, I guess I don't need to yet. First, I'll go back into GDB. So we'll say GDB classic. And now we're going to open the normal binary, not the debug binary. And we're going to read in this contents of normal.txt. And verify, yeah, even for the original binary, this works as well, overwriting the buffer. But the problem here is that we don't really know where in memory, at what offset, the return address is from our array that we're overreading into. So maybe you could do like, some math maybe and try and figure out based off like the size of the stack and everything, like the offsets of different variables, where the return address should be. But we have a better way of doing this, of determining like the offset from the array that we're overwriting that the return address is, so we know what to target. So just to be clear here, we're trying to figure out this distance, how far we should write to where we should place our new return address that we want to place into this return address here. How far away is the original return address from the memory address that the array is located at? We want to know where that is so that we can write directly to this specific address. The way to do this, we have like a few tools to do this that this GBD PEDA tool provides us with. One of them is this pattern create tool. So what this will do is actually create a pattern like a cyclical pattern of characters that we can use to help us find the position of that return address. So we're going to be, writing this pattern of data into the stack frame. We can actually look at that pattern and use that to figure out, well, based off what position in the pattern is written to the return address, that tells us what offset the return address is from the base of this array that we're overwriting. So let's actually try running this and reading in that pattern. And you can see like the cyclical pattern. It's filling up the stack now. So it seems like this is good. We'll be able to put our pattern into the stack. We can actually examine the values of individual registers with instructions like this. So we're going to say x/wx RSP. And what this will do is examine, the x means examine here, and hexadecimal representation, that's what the other x means, and word size, 32 bits on my machine, the place in memory that is stored, that is pointed to by RSP. So here we can see at this address, there is this value. So RSP presumably stores this address, and at that address there is this value, which is part of our cycle, our pattern that we'd created. So I've already disabled ASLR, so we can leave that off. Now what we're going to do next is call GDB here again. So actually, I think we're still in GDB, so we can leave this open for now. Let's see, anything else that we should do here? Okay. So we already ran the pattern. We already checked. The next thing we want to do is create this pattern, find the pattern offset at which this value is. And this is the same value as I have in my notes, which is good. So we're going to find the offset at which the pattern that we saw earlier is located. So I'm actually going to put the mic down so I can copy this. And now when we run this, it will tell us the address, the offset from our base pointer at which this return address is located. And we can see it's at offset 104. So that's the offset of the return address. So now let me go down here to this next illustration. What we're going to try and do is store at offset 104 in the return address here our payload. And what we're going to store here, to make it very clear that we're doing this correctly, we're going to store a bunch of A's, some letter B's right at the return address, and then follow it up by a few letter C's, just to make sure that we can correctly store values in this specific return address. So how are we going to do that? Well, let's scroll down here a bit more. We're going to use this find IP script. So let me quit GDB here so we can take a look at that. What this will do is use the struct library from Python to create a packed buffer here. So we're going to say, give us an empty string, fill it with 104 A's to take up the first offset to the RIP, or the instruction pointer. Overwrite that instruction pointer, the return address, with 0x424242. This is the hexadecimal for a sequence of B's. And this is, by the way, this is not enough to fully fill the number of bytes you want to pack in. So we're going to have some null characters appended to the end here. So be prepared for that. And then we also are going to add some letter C's as well to keep the original payload length at 400 bytes. So now let's try running this. And we can see that this is the contents of that, the payload of that that we're going to be delivering to the program now. This is what comes out of that find IP Python script that we just ran. And you can see these like unprintable characters here. These are just null bytes appended at the end to sort of pack out this space here. It has to be 32 bytes, but I'm pretty sure these B characters only take up 4, 8, 12, 16, 20, 28 bytes. So we need to put some characters in here to pad out this remainder. So we just use 2 null terminators here. 2 null characters, I suppose. Okay, now let's try running GDB again on that classic binary. And let's read in that find IP.txt. And we get a segfault, which is what we expect because we're overwriting the return address. And we see on the stack there's a letter C a bunch of times. The PC, the program counter address, has been set to 424242. So we were able to overwrite the return address. So this is B. And then I think, yeah, up here is A. So RBP, all the other stuff below is going to be A. So we successfully overwrote that specific portion of the stack with A, B's, and C's. And we can actually, just to make sure this is very clear, we can actually inspect the contents of RIP, the instruction pointer. And if we were able to overwrite the return address correctly, this should be at address, yep, there it is, 424242, 424242. So cool. Pretty nice. We got that working. So how can we actually take advantage of this? Well, we're almost there. Now what we need to do is, instead of filling this return address with a number of B's, we have to change this return address to instead jump to the address of this evil binary code we're going to be inserting into the environment variable here. So let's set up that environment variable now. We can do that. We can do that by copying this code here. I'm going to copy this and paste it in. What this will do is set the environment variable pwn. This comes from like the gamer world, getting pwned. To this string python2-c print, and we're just going to be printing out this this content here. This is actually like a shell substitution. We're going to be setting this to the hexadecimal code represented here. And what does that hexadecimal code represent? Well, it's actually like the binary or the hex encoding of some malicious assembly code. So if we can actually disassemble this and see what it actually looks like. So I'm going to copy this here. And what this disassemb command will do is disassemble the input you give it. So we're giving it some binary code. It's going to actually, or hexadecimal code, I should say. It's actually going to decode that and actually print out what the corresponding assembly code is. So it's, yeah. And you can see this is the actual assembly code we're putting into this payload now. And you can see we make a syscall at one point. That syscall is going to be to execute, I believe, a shell. There's some other syscalls here too. Yeah, I'm not exactly sure what this code does, but it is malicious. It's what we're trying to insert. So if all goes well, we're going to modify the return address to jump to the first instruction here of this assembly code, this like, assembled assembly code, object code essentially, and then start executing from there. So now what we have to do is actually change the return address to jump to this code, now that it's in our environment variable. So let's actually get the address of the environment variable itself, because we've modified the return address now. We were able to change that, but now we have to store in the return address the actual address of this environment variable. So we're going to run this script here, get-env, or program actually, get-env adder, which will actually tell us the address, the offset, or the address of that environment variable. And if we run this, we can see the address is going to be at this place here. So that's the address we're going to be targeting. And now we're going to modify this script exploit.py to have that address in it. And this is a little bit different, so let me fix this. You can see it's actually a different address than what it was earlier when I was testing this. I think that's right now. Yeah. You can see this is like the same as what we had before, right? For that findip.py script. Let me open that up again so you can check it out. They're like very similar, these two scripts. So the exploit one is on the right and findip is on the left, where we had packed these letter A's in and then the letter B's and then letter C's. The only difference is on the right here, we're actually going to be packing in the actual address this time of where we want our code to jump to, which is going to be inside that pwn environment variable. So I'll close this. So now we've created our payload. It's in that exploit.txt file. You can see right at the end here, that's going to be our return address inside the environment variable. And now we'll just ensure that this classic binary has the set UID set with root privileges. And let's just verify that. Okay, so you can see the S is here. That means it's set with a UI, with a set UID bit is set for this binary. And now what we can do is actually run the exploit. So what this will do is cat out the contents of the exploit.txt file, and then run cat again just to print out an end of line character, I believe. And then it's going to pipe that result, or end of file character, pipe that result to classic. And what should happen is, because that exploit contains the exploit.txt file contains enough to override our buffer and then change the return address to the beginning of that environment variable pwn, we should actually, upon running this, be placed into a shell that gives us root privileges. So if I run this, you can see it says buff is A and then no shell for you, but the program hasn't stopped running. It's suspended. It looks like it's suspended, but not really. It's actually, if we were to run a command here, you can see we have a shell. We have full access now to run commands. So I can run ls, I can run pwd, and get my current address. And to verify that I have the root privileges, I'm going to run who am I? And you can see we have root privileges. So we actually just compromise this machine, and from here you can do whatever the heck you wanted on this machine. You could just, copy all the files, like delete files, steal stuff, whatever you wanted to do. And not that you should do any of that, not that you even can do any of that, because we had to disable like ASLR, we had to disable stack canaries, we had to enable executable stacks for any of this to work. But it's still, I think, very empowering and exciting to know that the knowledge you have makes you a little bit dangerous, Yeah. So that wraps up the lecture. Now, what I'm going to do before I forget is set my, I'm going to quit this Docker container and set my ASLR back on. So I'll do that right now. Okay, so now that should be good. And yeah, that's it. So good luck. The next lecture we'll be going over final review. Again, this stuff's not going to be in the final. Stack smashing is not in the final. It's just very interesting, but it's not going to be in the final exam. This is not really essential to the course. It's just a cool application of what we've learned. So yeah, next lecture, final exam review, study, and make sure to complete your project resubmissions by May 2nd. I will see you all in the next class.